Maybe these are the two most important statements that we proved. We have some other. Okay, maybe this is. In general, the total Betti number, so the Betti number that you get in this, say, top line. So here, so far we're discussing zero or non-zero, right? Now let's say something about the number. So this number is at most t over I. So here, you know, we are really talking about the number of syzygies in degree 2i, homological position I. They are bounded by this binomial coefficient. This is, I mean, if you want, is beta 1, 2 of R. So the number of generators of the ideal which defines R. So along this top line, the total Betti number is bounded by this binomial coefficient. I mean, this is the statement here. Here is stronger. Here, I mean, we know that if it is LG quadratic, the total Betti number is bounded by this binomial coefficient. Okay. Here we are only saying the one on the top line, the one which is, if it is 0 at the position I, it will be 0 next. That number, no matter what it is bounded by this binomial coefficient. So okay, maybe the last statement. I'm right.
There are some examples that does not satisfy that. I mean, total Betti number. If LG are quadratic, then total Betti number is at most T choose R. Then you say it's Koszul and the top line Betti number satisfies the inequality. I want to know.
I think I also want to know. But I mean, if you find an ideal which is Koszul and does not satisfy this bound, we have found the example I was looking for, but I wasn't able to find it. I mean, and this is still open. I mean, let's say like this: what we really can keep under control are the degrees in which there is syzygies or not. Not so much about the number. So we can say in this degree there is something or there is nothing, but we don't know exactly the numbers. The numbers are really controlled only along the top line. Okay, I was saying also that what we know for sure, which is also a little bit expected, that this top Betti number, this is for sure 0 if you pass the codimension. So if I is larger than the codimension of R into S. So you may say dimension of S minus dimension of R. Okay, for instance, for a Koszul ring, this doesn't say anything because we know that the resolution will stop at this level. Okay, so for a Koszul ring, this is no meaning. But if the ring is non-Koszul, if you pass this codimension position, for sure you have to leave the top line. You cannot stay on the top line anymore. Okay. So these are, very somehow surprising statements because they say that, as I said before, the syzygies of this Koszul ring are, they satisfy many restrictions which are easy to see for rings defined by monomials by means of the Taylor resolution. All these restrictions are easy to see for rings defined by monomials of degree 2. But the Koszul ring, it is difficult to see, but still they satisfy this kind of restriction. And of course, what he was asking for is something which is at the moment still open. Maybe this might be an abstraction. This statement about the total Betty number. I mean, I was saying that in the paper it's difficult to get to realize that we prove this statement because we are study a more general problem. The more general problem is we don't have the polynomial ring first, but we have a Koszul ring to start with, and we take any quotient, need not to be Koszul. So we somehow generalize the frame, and then we have statements like this, that when you specialize to this situation, the numerator is not a general Koszul ring, it's a polynomial ring, and the quotient is Koszul, you get this bounds. I mean, the approach that we take in the paper is via some spectral sequences. Okay, the generation of spectral sequences. But if you just want this statement for this setting, there is a much easier approach, and which, I mean, which can be, I mean, described in terms of the Koszul homology of the ring R. So what one really can prove when those are consequences is the following: that if you take, okay, now we take the Koszul complex of a ring R, and with respect to its maximal ideal. So we know the homology of this complex gives us the syzygies. This is the usual statement that we have said several times. So the Betty numbers of S, of R over S, these are really the vector space dimension of this Koszul homology. Okay, now, we know that if we take the Koszul homology, this is a ring. So the ring structure allows us to say there is a map from the exterior algebra of H1 to the Koszul homology. Particularly in degree I have this map. Okay. It's just a multiplication map. We know that if I take two elements in degree 1, I can multiply them and get something in degree 2. I want to, of course, turn the multiplication into a linear map. So I take just the exterior algebra over H1 maps into HI.
So you have denoted the product by Ricci because the element of degree 1 is denoted by E1.
Sorry, I didn't get it.
So
why I take the, I could take.
So the degree 1 element is just like the Ricci element. So you denote the product.
Yeah, I mean, of course, the point is this. I mean, the multiplication map is not a linear map, right? It's a bilinear map or multilinear map. I want to turn it into a linear map, so I have to go through the tensor product. But of course, since I know that this is graded commutative algebra, really the equation that define the exterior algebra as a quotient of the tensor algebra, they go to 0 automatically. So I got map on from the exterior algebra, but it's not so important. You can also, if you like more the tensor, you can say the tensor, because what we are talking about now is an image. And the image is the same. So if you come from the tensor algebra or you come with the exterior algebra, the image is the same. Okay. So the nice thing that this map is surjective. If R is Koszul, this is under this assumption, this map is surjective, not surjective in general, surjective in degrees larger than or equal to 2i. Okay, which means that okay, let's see what we have. So this is a vector space which is graded and it is generated in degree 2. Okay, because this, the H1 is really refers to the syzygies. So this is, as a vector space, this is K shifted by 2. And how many copies do we have of K? How many? As many as the number of generators of the defining ideal. So this is the number that we have denoted by T so far. Okay, the minimal number of generators of the defining ideal of R. This is the H1. Okay, it's a vector space of rank T, but it comes with a degree structure. The generators are in degree -2. Okay. Now, when I take the wedge, I get a vector space in dimension, in degree 2i, and rank T, choose I. This maps surjectively on this guy in that degree and in that degree on. So this means exactly that below, over degree 2i, you have nothing because of this surjectivity. Okay? Once again, I mean, this vector space in dimension in degree j give us beta ij of R. So I want to say if j is larger than 2i, this is 0. Okay, but I know that there is a surjective map from a vector space which lives only in degree 2i. If I pass that degree, there is nothing on the left-hand side. So there must be nothing also on the right-hand side. Because the map is surjective above these degrees. This first gives the first statement, first vanishing statement. Secondly, if I know that at a certain level I have 0, in the next level I also have 0, because this map, I mean, is like the multiplication map. If I know that whenever I multiply 3 elements I get 0, it is also true whenever I multiply 4 I get 0, right? So this say, if you take saying that, suppose that we know that B3, 6 is 0. B3, 6, 0 means if I take wedge 3 of H1, this map is a 0 map, because we know it's surjective, and if it's 0 from this side, it must be the 0 map. Now the next map, B4, the next map is also surjective, because again, I mean, if the image from wedge 3 gives me 0, the image from wedge 4 gives me 0, because I can first compute wedge 3 and then multiply with an extra guy. Okay? So this says this kind of rigidity statement. If one is 0, the next is 0. Okay. And also this statement comes from this surjectivity, because in degree 2i, I have a surjective map from a vector space which has total dimension T, choose I. So, okay. And this is a little more complicated, so I don't want to enter in this. This really depends on the theorem. It's an application of the theorem of Brun's. Okay. Okay, so this was somehow the outcome of this investigation. And of course, the more you want, the more you have, the more you want. Right, here we have seen that there are unexpected restriction on the syzygies of Koszul ring, and we have also this statement that, I mean, I can grow like 2, 4, 6, 8 at most, but if I lose something at a certain point, that is lost forever. Okay. Then you can start to think what can be. I mean, what? Suppose we want to generalize a little bit this statement. What can be a nice generalization? A nice generalization is at each step you can make a jump at most by 2. Okay. So this somehow was a natural question that came out from. So one still open question is whether this bounds hold or not for a Koszul ring. And if we find a Koszul ring which does not satisfy this bound, we found the counterexample we were looking at. If we instead prove that every Koszul ring satisfies this bound, we again have proven some strong restriction on the syzygies of a Koszul ring. Somehow unexpected, at least. Unexpected in the beginning when you try to make up your ideas about the structure. Okay. But I was saying, okay, maybe it's better to introduce a name for the largest degree of the syzygies in the homological position I, because it's useful for this somehow kind of partial regularity. So these are usually called Ti because T refers to the Tor. Ti, this is the maximum of the J, such that beta I, J, R, S is non-zero. Okay, so we may rewrite this bound by saying Ti is less than 2I. Okay. Is the largest degree of the syzygies in the homological position I. So here we are saying if you are above 2I, you get 0. You may say it like this. And this second statement says Ti of R less than 2I implies TH less than 2H for every H larger than I. Okay. And this says something about the number, the total Bethe number, so it's not so, you cannot express it in terms of the T's. And this says that Ti is less than 2I if you pass the codimension. Okay. Now with this number, the natural question is whether you can say for a Koszul ring that you make at each step at each step is a resolution. You make at the most a jump of 2. Okay. So I have my set of quadrics. I know the first syzygies are linear. Let's say the first syzygies are linear, so the T2 is 3. Then we know that if the T2 is 3, the T3 cannot be 6 because I lost the top line. I will never reach it. For a Koszul ring, of course, we are talking about Koszul ring. But so it's more. So let's say an example. Suppose I have a ring which satisfies N3. N3 means, of course, T1 is 2, T2 is 3, T3 is 4. Okay. Okay. Suppose I have N3, so it means I have information. So what can we say about T4? If I use this bound, I know that T4, the first bound says it is at most 8. But the second statement says, since I lost the top line, I will never reach to at most 7. Right? So this bound T4 is at most 7, we know already. This we know. T4 is at most for a Koszul ring, of course. If you get rid of the Koszul assumption of the ring, is much more wild, the behavior of the syzygies. Okay, so you can have quadrics generated, and the first syzygy should be in very high degrees. Who knows? So this somehow low degree statement comes from the Koszul property. So here we say at most 7 we know, but here what I'm asking, since the T3 is 4, I'm asking whether the T4 is at most 6. Because I ask whether there is at most jump of 2 at each step. So since I have lost 2 from the top line here, I will stay below that line from that point on. So the question that I'm making here is, in this case, if the T4 is bounded by 6. Okay.
What do you mean N3?
N3 means this. Exactly what it means. It means that the syzygy will stay linear for 3 steps. You have a set of quadrics, and for 3 steps you will have linear syzygies. Okay. I mean, it's. I said N3 because I know that in most of the audience is very familiar with this terminology. So I want to, say something which was, familiar with many of you. Okay, so this is the state. Is it true or not for the Koszul ring? And I said, this 2 is T1, right? This 2 is T1. So here I'm saying Ti plus 1 bounded by Ti plus T1. Maybe, of course, asking question is easy. You can say, can we say that more general? Maybe I want that Ti plus J R S is bounded by Ti over plus Tj. Maybe that's Koszul. For a Koszul ring. Okay, so these are still open questions. Both the first one and the second one.
For any I and J.
For any I and J, of course. As long as you ask questions, you can, you are free to, for every I and J. And as I said, Z1 is J equal 1, right? Because if I plug in J equal 1, T1 is 2 in this Koszul setting. So somehow we are saying that some information in the beginning of the resolution tell me something on the remaining part of the resolution. This is already what is happening. Yeah, we are a statement like this saying exactly that. If I know that something in the beginning, for instance, I have property N2, meaning T2 is 3. This fact will have consequence for the rest of the resolution. I will never be able to reach the top line if I lose it in the beginning. So something in the beginning has effect throughout the resolution. So also here we are saying this in a more stronger way. The surprising thing that these statements, they are open also for the rings defined by monomials of degree 2. So even for the class that we treat as, this is an easy case that we do right away just to have an idea what's going on. For the real rings we like to look at, which are coordinate rings of varieties, for instance. Even for this combinatorial setting, these are open questions as long as I know, as far as I know. Okay. So these are really very likely very difficult to treat in general, and maybe false, who knows. But I mean, somehow the guiding idea is this must be a reflection of some statement on the multiplication structure of the Koszul complex, Koszul homology. Because maybe, I mean, as I said here, this was somehow after some discussion, it was something which referred to the multiplication map from the exterior power of H1 into HI. So maybe there is something, some nice statement which refers to, you take HI, MR, R, tensor HJ, MR, R, and you go into, well, the multiplication map leads you into the HI plus 1, MR, R. So maybe we are saying that this map is surjective in certain degrees. If we are able to say that this map is surjective in certain degrees, we get a statement like this. Because here the top degree in which this is non-zero is this number. Okay? Because this vector space lives up to degree Ti. This vector space, these are tensor product of the field. This vector space lives up to this degree, so the tensor product lives in, at most in this degree. Indeed, exactly in this degree. The top component of this vector space is in this degree. And this vector space lives, by definition, in this degree. So if we can say that this map is surjective in certain degrees, we are bound to get statement of this kind. Maybe not exactly this one, but
can you determine the same I plus j is same, and we can choose different ij. Which one is the bigger?
His question is here. I mean, I plus the same number, say 10, can be written I plus j in many ways, right? 5 plus 5, 4 plus 6, 3 plus 7. What is the best upper bound that you get? This I don't know. I mean, it very much depends. I mean, if you try to, I mean, for instance, I tried to play this game. Let's assume this is true. And suppose my ring satisfies NP for a certain P. What do I deduce? Because, you know, I can iterate this thing. I mean, I can, if I know it for 2 factors, I know it's for more. Because like each one of these, like I write, T10 equal T4 plus, bounded by T4 plus T6. But then the T6, I can say it's at most T3 plus T3. So I can get more and more formulas of this kind. So if I assume the property NP, so the first few steps is linear, I can say something about the remaining part of the solution. And it's difficult to say which kind of combination do I have to take of numbers to get the best bound. But I mean, this is something that, I mean, I made this, say, experiment, and I saw some restrictions that this looks too restrictive, so to say. I mean, so I don't believe completely in this inequality. So but I mean, so far, I mean, I have not been able to find counterexamples, and not even, I mean, and I checked many cases, even rings defined by monomials is easy because the resolution is quick. To compute the resolution of rings defined by monomial, the resolution you get quick, and then you compute this inequality, and as long as I was able to compute, this seems to be okay. But the experience says the first best thing can happen in a dimension where you will never make a computation with a computer. Like maybe the first example is with 100 variables, you will never find it with a computer. So I mean, we should not somehow believe too much in what we say, in what we see in the initial range, because this might be some misleading evidence. Okay. So this is a question, and we can get some result in this direction. Some result which, I mean, I think they are nice, and So we are still, this is still work in progress, which I'm doing with same two co-authors, Avramov and Yanger. This time the main contribution comes from my own understanding of the Koszul homology. And maybe I just tell you one result that you can prove for sure. Then there are others which are, which are being discussed exactly in these days. So we can prove at the moment a formula of this kind, not exactly this formula, a formula of this kind. And in one case it looks nice. It is the following. Suppose that R is Koszul and Koimekoli. Okay, this Koimekoli assumption is simplifies the argument, because under the Koimekoli assumption you know that the T's, they form a strictly increasing sequence. So the reason why I put this assumption here is because under the Koimekoli assumption we know that the syzygies, they strictly grow until you reach the TH. Okay. In general, it might happen that sometimes you go down. Okay. This can happen if you are in the non-Koimekoli case. Okay.
How about within the codimension, they can drop?
No. In this range, they cannot drop. In this range, they cannot drop, even with or without the Koimekoli assumption. So this,
You think about the whole bet, any.
So the point is that for the Koimekoli there is no other Betti number if you pass this point. For the non-Koimekoli it can go up. Okay? And in the next steps it can also go down from time to time. Okay, so either we talk about Betti numbers within the codimension, and then the statement holds for all, or we talk about all the Betti numbers, but I assume the Koimekoli property. Maybe we can say it like this. Let's say it like this. No Koimekoli assumption, but we talk about the Betti numbers within the codimension. So from 1 to h, where h is the codimension, if we pass that line, we don't know what's going on. So if it's Koszul, then we know that ti plus 1 is bounded by ti plus 2, then provided we stay below the codimension. Okay, this is the statement. So the jump is at most by 2. It was exactly that statement over there. It's a codimension. The codimension of R, meaning the dimension of the polynomial ring minus the dimension of R, or if you want, the height of the ideal. Okay. So this is something that we can prove. New result. 2012, maybe 13. And same author. Okay. Where? Where? What where?
What's your name?
Not decided.
The year?
No. Which
Did you
Which
have
genre?
Which
I
genre?
wanna-
Journal of Future Mathematics. I don't know. At the moment, we are in the stage where we are really getting results, and in the beginning you don't want to write right away what you have, but you expect to improve the result that you have. Okay. So, but let's say, for instance, for the coordinate ring of the Veronese variety, it's Koszul ring, we know, because it is defined by a Gromov maze of quadrics. It's This is Koszul, so we don't have to worry about passing the codimension. There is no Betty numbers if you pass the codimension. So the resolution of the Veronese coordinate ring is not known. Some bounds are known, but there is no general expression for the i's, j Betty number. So here we are saying that in a certain homological position, I have at most syzygy in degree so and so. In the next, it must go up for sure because it's Koszul, the largest degree, by 1 or by 2. These are the only options. Cannot go up by 3. No, this is impossible. Either by 1 or by 2. This is what we are saying here for a Koszul ring. And this kind of bounds, they are far from being true for non-Koszul rings defined by quads. So we are really somehow more and more finding restriction on the syzygies of this family of algebras. Okay, so this was somehow what I want to say concerning this investigation. As I said, it started by looking at counterexamples, but the more we look for counterexamples, the more we found restriction on the syzygies of the algebra we are looking at. Okay, maybe it's. Did I start at 2 or 2:30?
2:30.
I started at 2.
We start 2.
I started at 2. So it's.
3:30 is fine.
3:30 is fine. Okay, so tomorrow I will talk about the problem of deciding whether the certain rings are Koszul or not, and specifically the projection of the generic projection of the Veronese surface in P9. So you take Veronese surface in P9 and you project down to P8, and the question is whether you get Koszul ring or not. So this question sounds a little bit special. Why P9 and P8? Why the Veronese surface? But somehow it was a benchmark case. It was open for a long time and was supposed to be, one of those problems that if you have a new technique, you want to test it, it's one of those test cases. I mean, for 15 years was open, if one finds a technique which solves that case, it means this is a new technique. Okay, and tomorrow we'll talk about that result. Okay.